Welcome! In this session, we'll explore problem number 2087, minimum cost homecoming of a robot in a grid. This problem challenges us to find the optimal path for a robot to return home in a grid while minimizing the cost. We'll cover various approaches to solve it, analyze their complexities, and extract important takeaways. Let's dive in. In this problem, we are working with a grid that has dimensions mxn. A robot is initially positioned at a specific cell, represented as start_x, start_y, and it needs to move to its home cell, located at home_x, home_y. The robot can move in any of the four cardinal directions: up, down, left, or right. However, each move comes with a cost. Moving up or down incurs a cost defined in the row costs array, where each entry corresponds to the cost of moving into a particular row. Similarly, moving left or right incurs a cost defined in the call costs array, where each entry corresponds to the cost of moving into a particular column. The robot must stay within the boundaries of the grid, and our goal is to calculate the minimum total cost required for the robot to travel from its starting position to its home position. The output for this problem is a single integer, which represents the minimum cost of moving the robot from its starting cell to its home cell. Let's take a look at some examples to better understand how this works. In the first example, the robot starts at 1, 0, and needs to reach 2, 3. We are provided with the following costs: row costs equals 5, 4, 3, and call costs equals 8, 2, 6, 7. Based on these inputs, we will determine the steps the robot takes and calculate the cost of each move. To move from 1, 0 to 2, 3, the robot first moves down to row 2. This incurs a cost of row costs 2 equals 3. Next, the robot moves right, entering column 1, which incurs a cost of call costs 1 equals 2. It continues moving right to column 2, incurring call costs 2 equals 6, and finally moves right one more time to column 3, incurring call costs 3 equals 7. Adding these costs together, the total cost is 3 plus 2 plus 6 plus 7, which evaluates to 18. This is the minimum cost for the robot to reach its destination in this scenario. In the second example, the robot starts and ends at the same cell, 0, 0. The input costs or row costs equals 5, and call costs equals 8. Since no movement is required, the total cost is simply 0. This demonstrates that if the robot's starting position is the same as its home position, no cost is incurred, as no steps are taken. In the third example, the robot starts at 3, 3, and needs to move to 0, 0. The input costs or row costs equals 1, 2, 3, 4, and call costs equals 1, 2, 3, 4. The robot begins by moving up to row 2, which incurs a cost of row costs 2 equals 3. It continues moving up to row 1, with a cost of row costs 1 equals 2, and then up again to row 0, incurring row costs 0 equals 1. After reaching the correct row, the robot moves left to column 2, adding call costs 2 equals 3 to the total. It moves left again to column 1, adding call costs 1 equals 2, and finally moves left to column 0, adding call costs 0 equals 1. Summing these costs, the total is 3 plus 2 plus 1 plus 3 plus 2 plus 1, which equals 20. There are a few important constraints and edge cases to consider in this problem. First, the dimensions of the grid, m and n, can be as large as 100,000, so the solution must be efficient to handle such large inputs. Additionally, the movement costs specified in row costs and call costs can be as high as 10,000. So it's important to ensure that the algorithm correctly accumulates these costs without encountering integer overflow. Edge cases include scenarios where the robot starts and ends at the same position, resulting in zero movement and zero cost, and situations where the grid is a single row or column. In such cases, the robot can only move in one direction, simplifying the problem. Lastly, for grids with high movement costs, the solution must still optimize the path to minimize the total cost while adhering to the constraints. To tackle this problem, we initially consider a brute force approach, which involves simulating every possible path the robot could take from its starting position to its home. While this method is straightforward and easy to conceptualize, it quickly becomes computationally infeasible. The reason lies in the sheer number of potential paths, as the robot has multiple movement options at each step. For a grid with dimensions m by n, the possible paths increase exponentially, leading to an overwhelming number of combinations. However, a key observation here is that moving directly in one direction, either all horizontal moves followed by all vertical moves, or vice versa, eliminates redundant steps and simplifies the problem significantly. Despite these insights, the brute force approach still has exponential time complexity, making it unsuitable for larger grids. This motivates us to consider smarter alternatives, such as a greedy strategy. A more efficient alternative is the greedy approach, which leverages the properties of grid movement to minimize the cost. Here, the robot moves in straight lines either horizontally or vertically without unnecessary detours. The total cost is calculated by summing the horizontal and vertical movement costs separately. First, we compute the horizontal distance by taking the absolute difference between the home and start column indices and multiplying it by the cost of horizontal moves. Similarly, we calculate the vertical distance by finding the absolute difference between the home and start row indices and multiplying it by the vertical move cost. Adding these two values gives the total cost. Importantly, the order of movement doesn't matter, as the cost depends only on the Manhattan distance between the two positions. This approach is highly efficient, with a constant time complexity of 1, and it simplifies the problem without compromising accuracy. The optimized greedy approach is the ideal solution for this problem due to its efficiency and simplicity. Unlike the brute force method, which is computationally expensive, the greedy approach runs in constant time, requiring only basic arithmetic operations. This makes it highly scalable, even for the largest grid sizes. The implementation is straightforward, as it avoids complex techniques like recursion or dynamic programming, and it does not require additional data structures. Beyond simplicity, the solution guarantees correctness because it directly calculates the minimum cost based on the Manhattan distance and the given movement costs. Compared to brute force, which is conceptually simple but impractical for large grids, the greedy approach achieves the same result with far greater efficiency. Unless the problem constraints change, such as introducing diagonal moves, this approach remains optimal. Overall, the optimized greedy strategy balances correctness, simplicity, and efficiency, making it the best choice for solving this problem effectively. To solve the problem of finding the minimum cost for the robot to move from its starting position to its home position, we first need to define the problem clearly. The robot is tasked with navigating a grid, starting at coordinates start_x, start_y, and reaching a target position home_x, home_y. Each movement direction incurs a predefined cost, which means our goal is to find the path that minimizes the total cost. We'll represent the grid as a 2D matrix, where each cell stores the cost associated with moving through it. Additionally, the starting and home positions are explicitly defined by their coordinates. To handle this problem efficiently, we initialize key data structures. A priority queue, specifically a min heap, will allow us to always expand the least cost node first. We'll also use a cost dictionary to store the minimum cost of reaching each cell in a visited set to ensure we don't waste time revisiting nodes we've already processed. These foundational steps set up the framework for our algorithm. Next, we design the movement logic for the robot. The robot can move in multiple directions, so we define all possible dx, dy pairs that represent these moves. For example, 0, 1 represents moving right, while 1, 0 represents moving down. For each move, we calculate the cost of transitioning to the neighboring cell. With this movement logic in place, we can now execute the algorithm itself using Dijkstra's approach. The process begins by pushing the starting position, start_x, start_y, into the priority queue with an initial cost of 0. The algorithm then iteratively processes nodes, always expanding the one with the lowest cumulative cost first. If the current node matches the target position, home_x, home_y, we return the cost, as this is the optimal path. Otherwise, for each neighbor of the current node, we calculate the cost to reach it. If the neighbor hasn't been visited yet or we discover a cheaper path to it, we update its cost in the cost dictionary and add it to the priority queue. This ensures we're only expanding the most promising paths at each step. Once the algorithm completes, we output the result. If the target node is reached, we return the total accumulated cost as the solution. However, if the priority queue is exhausted, meaning no valid path exists to the home position, we return an appropriate message such as path not possible. A few key insights make this approach both efficient and reliable. First, the use of a priority queue ensures greedy expansion, always prioritizing nodes with the lowest cumulative cost. This guarantees optimality as long as movement costs are non-negative. Second, the visited set avoids redundant processing by ensuring we don't revisit nodes we've already handled. Finally, the cost dictionary dynamically tracks the shortest known path to each node, allowing efficient updates whenever we discover a better route. These principles collectively ensure the algorithm performs well, both in terms of correctness and computational efficiency. The efficiency of the algorithm is heavily dependent on the data structures we use. The priority queue, implemented as a min heap, is critical for retrieving the node with the lowest cost in logarithmic time. This ensures that we always expand the most promising node first. The cost dictionary, on the other hand, is used to store the minimum cost required to reach each cell in the grid. With constant time lookups and updates, it allows us to dynamically track progress and avoid recalculating costs for nodes we've already evaluated. Finally, the visited set keeps track of nodes that have already been processed, ensuring we don't revisit them and waste computational resources. Together, these data structures work in harmony to make the algorithm both time and space efficient, enabling it to handle even larger grids effectively. To further optimize the algorithm, there are several advanced techniques we can apply. One option is to incorporate a heuristic into the search process, turning it into an A** algorithm. By prioritizing nodes that are closer to the target, we can reduce the overall number of nodes explored. Another optimization is the early exit strategy, where we terminate the algorithm as soon as the target node is dequeued from the priority queue. This eliminates unnecessary processing of additional nodes. For sparse grids, using adjacency lists instead of a full 2D matrix can significantly reduce space complexity. Finally, if movement generally occurs in specific directions, we can introduce a directional bias by prioritizing neighbors in those directions during exploration. These optimizations can make the algorithm even faster and more efficient, particularly in scenarios with larger grids or specific movement patterns. The provided Python implementation solves LeetCode problem number 2087, minimum cost homecoming of a robot in a grid. The goal is to compute the minimum cost for a robot to move from its starting position to its home position based on row and column movement costs. The function minCost takes four inputs: start_POS, the robot's starting coordinates, home_POS, the robot's home coordinates, row_costs, an array representing the cost of moving through each row, and col_costs, an array representing the cost of moving through each column. The algorithm proceeds as follows. 1. Extract positions: the start_x, start_y, home_x, and home_y are extracted from start_POS and home_POS for clarity and readability. 2. Initialize total cost: a variable total_cost is initialized to 0. This will accumulate the total cost of the robot's movement. 3. Vertical, row-wise, movement. If the robot needs to move downward, from start_x to home_x where start_x home_x, we iterate from start_x plus 1 to home_x and add the respective row_costs for each row. Similarly, if the robot needs to move upward, from start_x to home_x where start_x home_x, we iterate in reverse, from start_x 1 to home_x 1, and sum the respective costs. 4. Horizontal, column-wise, movement. If the robot needs to move rightward, from start_y to home_y where start_y home_y, we iterate from start_y plus 1 to home_y and add the respective col_costs for each column. Similarly, if the robot needs to move leftward, from start_y to home_y where start_y home_y, we iterate in reverse, from start_y 1 to home_y 1, and sum the respective costs. 5. Return total cost. Finally, the accumulated total_cost is returned as the result. This approach ensures that all movement costs are considered, and the robot takes the most cost-effective route. The implementation handles edge cases such as when the robot's start and home positions are already aligned in either rows or columns, as no unnecessary costs are added in such scenarios. Here, we begin by defining a class called solution and implementing the minCost method. This method takes four parameters: start_pos and home_pos, which represent the starting and target positions of the robot, and row costs and call costs, which specify the cost of moving through each row and column in the grid. First, we extract the starting and home positions into separate variables to make the code more readable. Then, we initialize a variable total cost to 0, which will accumulate the total movement cost. Next, we calculate the cost of moving vertically, or row-wise, from the starting row to the home row. If the starting row, start x, is less than the home row, home x, it means we need to move downward. In this case, we iterate through all intermediate rows between start x and home x, adding the corresponding row costs to total cost. Similarly, if start x is greater than home x, we need to move upward. Here, we iterate in reverse through the rows, decrementing the index and adding the row costs along the way. Now, after calculating the vertical movement cost, we proceed to determine the horizontal cost of moving column-wise from the starting column to the home column. If the starting column, start y, is less than the target column, home, we iterate forward through the columns, adding the corresponding column costs to total cost. On the other hand, if start y is greater than home, we move leftward by iterating in reverse and accumulating the column costs. Finally, after computing both the vertical and horizontal movement costs, we return the total cost variable, which represents the minimum cost required for the robot to move from the starting position to the home position. This approach ensures that we calculate the cost efficiently by leveraging simple loops and the provided row and column cost arrays. To solve this problem, we start by analyzing the given input. The robot begins at position 1, 1, and needs to move to the home position at 3, 2. The row costs and column costs arrays represent the cost of moving through specific rows and columns, respectively. First, we extract the starting and home positions. Start underscore x is 1, start underscore y is 1, home underscore x is 3, and home underscore y is 2. We then initialize the total cost to 0, as no movement has been made yet. Now, we handle the vertical movement, where the robot moves row-wise from row 1 to row 3. Since it moves downward, we calculate the cost for rows 2 and 3. The cost for row 2 is row underscore costs, 2, which is 3, and for row 3 it is row underscore costs, 3, which is 4. Adding these to the total cost results in 7. Next, the robot moves horizontally, column-wise, from column 1 to column 2. This involves adding the cost for column 2, which is col underscore costs, 2, equal to 7. Adding this to the total cost results in 14. Therefore, the final cost for this example is 14. In this example, the robot starts at position 2, 3, and needs to move to the home position at 0, 0, with new row and column cost arrays provided. We first extract the starting and home positions. Start underscore x is 2, start underscore y is 3, home underscore x is 0, and home underscore y is 0. Again, we initialize the total cost to 0 before evaluating the movements required. For the vertical movement, the robot moves row-wise from row 2 to row 0. Here, the movement is upward, so we calculate the costs for rows 1 and 0. The cost for row 1 is row underscore costs, 1, which is 2, and for row 0 it is row underscore costs, 0, which is 4. Adding these values gives a total cost of 6. For the horizontal movement, the robot moves column-wise from column 3 to column 0, moving leftward. We include the costs for columns 2, 1, and 0. Column 2 has a cost of col underscore costs, 2, equal to 5, column 1 has a cost of col underscore costs, 1, equal to 3, and column 0 has a cost of col underscore costs, 0, equal to 8. Adding these values to the total cost results in 22. Thus, the final cost for this example is 22. In this scenario, the robot starts at position 0, 0, and is already at the home position 0, 0. The row and column cost arrays are provided, but since there is no movement required, the steps are straightforward. We extract the starting and home positions, finding that start underscore x is 0, start underscore y is 0, home underscore x is 0, and home underscore y is 0. The total cost is initialized to 0. For vertical movement, as the starting row is the same as the home row, no movement is needed, so the total cost remains 0. For horizontal movement, since the starting column is the same as the home column, no movement is required here either. The total cost remains 0, as no additional costs are incurred. With no movement in both directions, the final cost for this example is 0. When analyzing the time complexity of this solution, there are two main operations to consider: the robot's vertical movement along the rows and its horizontal movement along the columns. First, let's focus on the vertical movement. Here, the robot travels from its starting row, start_x, to its target row, home_x. The number of steps it takes is determined by the absolute difference between these two positions, represented as abs, home_x, start_x. For each of these steps, the algorithm accesses the row_costs array to fetch the associated cost. Since accessing an array element is a constant time operation, O(1), the total time complexity for this vertical traversal is proportional to the number of steps, which is O, abs, home_x, start_x. Next, for the horizontal movement along the columns, the process is similar. The robot moves from its starting column, start_y, to the target column, home_y, taking abs, home_y, start_y, steps. At each step, it accesses the call_costs array to retrieve the corresponding cost, which is also an O(1) operation. Therefore, the time complexity for horizontal movement is O, abs, home_y, start_y. Now, combining these two independent operations gives the total time complexity of the solution. Since the vertical and horizontal movements occur separately, their contributions are additive. This means the total time complexity of the algorithm is O, abs, home_x, start_x, plus abs, home_y, start_y. In the worst case scenario, the robot may need to traverse the entire grid in both dimensions. Here, abs, home_x, start_x, could equal the total number of rows, n, and abs, home_y, start_y, could equal the total number of columns, m. This results in a worst-case time complexity of O, n plus m. Shifting to space complexity, the analysis is straightforward. The input includes the row_costs array of size n and the call_costs array of size m, but these are part of the input itself and don't count towards auxiliary space complexity. As for the algorithm, it uses a constant amount of extra memory to store variables like start_x, start_y, home_x, home_y, and total_cost. No additional data structures are used, which means the auxiliary space consumption remains constant. Altogether, the total space complexity of the solution is O(1), as the algorithm only requires a fixed amount of memory regardless of the size of the grid. To put this into perspective, let's compare this optimized solution with a brute force approach. A naive method would involve iterating over the entire grid, calculating the total cost for every possible path. This would result in a time complexity of O(n*m), which is highly inefficient for larger grids. In contrast, the current solution avoids unnecessary computations by directly moving from the starting position to the home position along the shortest path, achieving a much more efficient linear time complexity relative to the movement distance. Finally, when considering the best, average, and worst cases, the time complexity remains consistent. The number of steps the robot takes is always determined by abs, home_x, start_x, plus abs, home_y, start_y, which doesn't depend on the specific input distribution. This means the time complexity in all cases is uniformly O, abs, home_x, start_x, plus abs, home_y, start_y. When working on this problem, there are several common mistakes to watch out for. First, ignoring edge cases can lead to incorrect results. For example, if the starting and home positions are the same, or if the robot's movement is constrained by obstacles, it's easy to overlook how these situations affect the solution. Testing your code against edge cases is essential. Another critical mistake is relying on a brute force approach. While it might seem intuitive, brute force methods often result in exponential time complexity, such as O(2)m plus n, for grid problems, which is impractical for larger inputs. Instead, focus on optimizing your approach. In recursive or dynamic programming solutions, incorrect base cases are another frequent pitfall. Forgetting to define scenarios like reaching the destination or encountering a blocked path can lead to infinite recursion or wrong answers. Finally, beware of integer overflow in languages like C++ or Java. Large grid dimensions or cost calculations can exceed standard integer limits, so using long data types or modular arithmetic is critical to avoid this issue. Misinterpreting problem constraints is another trap to avoid. For instance, if you assume diagonal moves are allowed when they aren't, or fail to account for negative costs, your solution might fail for certain inputs. Always clarify the constraints before you start coding. Speaking of interviews, it's important to confirm the movement constraints explicitly, such as whether movements are limited to up, down, left, and right, or if diagonal moves are included. This distinction significantly influences your approach. For optimization problems, break them down systematically. Consider dynamic programming for grid-based solutions or Dijkstra's algorithm for weighted graphs. If the grid is very large, think about space optimization. For example, you can reduce a 2D table to a 1D table or use in-place updates to save memory. During interviews, it's also a good idea to highlight trade-offs. Discuss the balance between brute force and optimized solutions to show your understanding of time versus space complexity. Finally, consider proposing variations, such as handling obstacles, variable movement costs, or even extending the problem to 3D grids. This demonstrates your ability to think critically and adapt solutions to new challenges. This problem is closely related to several other grid-based problems that you might encounter. For example, in LeetCode 62, unique paths, the goal is to count the number of unique paths from the top left corner to the bottom right corner of a grid. It's a classic dynamic programming problem. LeetCode 63, Unique Paths 2, builds on this by introducing obstacles on the grid, which must be accounted for in your path calculations. Another related problem is LeetCode 64, Minimum Path Sum, where you find the path with the minimum sum of values from the top left to the bottom right of the grid. Lastly, LeetCode 980, Unique Paths 3, is a more complex variation where you must count paths with specific start and end points, ensuring that all cells are visited exactly once. These problems share similar techniques and concepts, making them excellent practice for mastering grid-based algorithms. There are several alternative approaches to solving grid-based problems like this one, each with its own trade-offs. Dynamic programming is a highly effective method that breaks the problem into smaller subproblems and stores intermediate results to avoid redundant calculations. While its time complexity is O(m*n), it can be space-intensive if a full grid is used. Breadth-first search, or BFS, is another option, particularly for unweighted grids with obstacles, although it's generally less efficient than dynamic programming for optimization problems like minimizing costs. For weighted grids where movement costs vary, Dijkstra's algorithm is a powerful choice. It's well suited for these scenarios but comes with higher time complexity, typically O(m*n)log(m*n). Finally, recursive backtracking can be an intuitive approach, but it's often impractical due to its exponential runtime. Combining it with memoization can make it feasible for smaller grids, but it's unlikely to perform well on larger inputs. Understanding these options and their trade-offs is key to selecting the right approach for different problem variations. Thank you for staying with us through this problem. To recap, we explored strategies to solve the minimum cost homecoming of a robot in a grid problem. We discussed key approaches, their complexities, and critical takeaways. Don't forget to apply these concepts to similar problems and keep practicing. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!